It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Finding Doing Nice Coffee. Hi guys, welcome to this video, which is going to be all about ion exchange chromatography. So I really strongly encourage you that if you haven't watched the video that covers the principles of chromatography, that you do that first, because it's important you understand about things like stationary phase, mobile phase, adsorption to the stationary phase, attraction to the mobile phase. All of those things come into play with ion exchange chromatography. So this is kind of right towards the end of that topic. If you haven't watched those videos, I suggest you do so. You may also want to be watching some videos around equilibrium, because I'm going to be talking a little bit about equilibrium and the Chatelier's principle there. So if you haven't watched something around equilibrium, you might want to look at that as well, or maybe come back and revisit this once we've done the equilibrium topic. Alright, so in ion exchange chromatography, we still have a stationary phase, as you'd expect, but the stationary phase in ion exchange chromatography is a resin. Okay, now there's two types of ion exchange chromatography you can have, which is cation exchange and anion exchange. So a cation is a positively charged ion, and anion is a negatively charged ion. So if we're doing cation exchange chromatography, we're exchanging positively charged ions with other positively charged ions, which is what we're looking at here today. So in cation exchange chromatography, the resin is actually negatively charged. Okay, so we've got our resin that goes through here, and on the surface of our resin we have cations. So in this case here we've got some sodium ions which are on the surface here of our resin. Okay, and this is our column that we're going to be passing our mobile phase through. Okay, so this resin here is our stationary phase. It's negatively charged in this case, and it has positively charged sodium ions on the surface. All right, and our mobile phase is going to flow down through the top and out the bottom of our ion exchange chromatography column. Okay, now what you've got to understand in chromatography for ion exchange chromatography is that we're replacing one positive charge with another positive charge here. Okay, so when you look at proteins, okay, here's an example of a protein, okay, and you can see here, sorry, I'll show you the neutral version first. So here's an example of a protein. Okay, this is alanine here. Okay, so you can see we've got some amine groups, we've got a carboxylic acid group here, and this is at neutral pH, so this has no charge. However, if you put it in low pH, what happens is the nitrogens here actually protonate, okay, and become positively charged. Now I suggest if you want a bit more information about that, you look at the video on proteins and what happens at low and high pH, because that'll explain that, and ion chromatography really brings together a number of different concepts. But when we positively put it in a low pH, we protonate the amines and we get this positively charged amino acid here. Okay, and so if we want to separate solutions of amino acids, which is quite common, or proteins I should say, we can use ion exchange chromatography, but they need to be charged, okay, the proteins or the molecules that we're using. So here an example, if this is our protein, rather than having this big thing, we're going to represent it by one of these blue shapes here. Alright, so we've got our protein that comes through with our mobile phase. Okay, and what happens is that this proton has a pretty high charge density. Okay, so it's got lots of positive charge. So what it does is this protein comes in and it actually binds itself to the surface of the negative resin. Now what happens is that as it does that, it displaces sodium ions from the surface. Okay, so we replace the sodium ions on the surface and they come out and we bind a protein to it. Likewise, when the next one comes in, that comes in and it takes away some of the sodium. Okay, the next one comes in, that binds to the surface, takes away some more of the sodium, binds to the surface, takes away some more of the sodium. So you can see how as our mobile phase comes through, the molecules that are inside our mobile phase slowly work their way down, displacing ions off the surface of the resin as we go. Now we get to a point where we've actually established an equilibrium. Okay, where we've got an equilibrium between the number of original cations on the surface of the resin and the number of, in this case, proteins that we've got on the surface of the resin as well. And so what we want to do now is we want to try and flush out these proteins that are remaining on the surface of the resin, because we want to collect these at the end and have them separated, okay, from the rest of the materials. And so what we do is we take a concentrated solution of the original cation. So in this case we have sodium, so we're going to flush this solution with a very concentrated solution of sodium ions. Okay, now what happens is that these sodium ions come in, and because there's such a high concentration, okay, they actually come back and replace the proteins at the surface. Okay, so the proteins start to come off and move down, okay, and the sodiums come in and replace, okay, at the surface of the resin, and that's called recharging it. We've got it ready for the next use. So the principle of it is that the molecules you've got within your mobile phase will adsorb or attract to the surface of your resin at different rates depending upon their charge density. So the more highly charged they are, the stronger they will attract to the surface of the resin, providing their opposite charge. Okay, so the more strongly charged, positively charged this is, the more strongly it attracts to the surface there, and the slower it will move through the column. If it's only got a very weak positive charge, it won't be very strongly attracted to the surface, and it will go through the column reasonably quickly. And then what we do is we get rid of the really highly positively charged ones by reflushing it with the original cation that we had on the surface of the resin, and we collect our protein or our samples at the bottom, and we've got our ion exchange chromatography column ready to go again. So what I mean by that equilibrium that exists is this. Okay, so you've got your resin, which is negatively charged. Okay, on the surface of your resin, you have those sodium ions. Now what we're doing is we're bringing in some protein here. All right, so we've got our resin and our protein, okay, which is positively charged there, and we have an equilibrium that exists where the protein goes onto the surface of the resin, and we get the sodium ions over here. Okay, so this is our equilibrium that we've got set up here. Okay, as we bring in the positively charged molecules, they replace the cation that's on the surface of the resin, and we get an equilibrium set up. Now, an equilibrium can go both ways. So once we've reached our equilibrium state, the concentrations don't change. Okay, and so what we were saying is that as we bring in a whole bunch of sodium again here, so we flush it with sodium. All right, what it does is it saturates this side of the equation with sodium. So according to Le Chatelier's principle, the equilibrium is going to shift to decrease this sodium we've just brought in. So how does it decrease this sodium that we've just brought in? Well, it does that, which is this free sodium, by binding it to the surface of the resin, which goes back to then form our resin with the sodium ion on it, and so we've regenerated it. And that's the principle behind that final recharging of the system, or flushing out of the very highly positively charged cations which are on the surface. Alright, so that's ion exchange chromatography, and that's cation exchange chromatography that we've done. Obviously, anion exchange chromatography just uses a positively charged resin with a negative anion on the surface, and we exchange anions in solution, but it's the same principle. So, how strongly one of your molecules absorbs to the surface of the resin determines how fast it moves through the column, and the more strongly it's attracted, the slower it moves, so you can separate all your components similar to other chromatography. But we use this sort of chromatography when we have charged molecules in our mobile phase, all right, as opposed to things like high-performance liquid chromatography or gas chromatography where your molecules are uncharged. And this always uses a solid stationary phase of the resin and a liquid mobile phase. So hopefully this has made sense for you. I suggest you go back and have a look at it again, and as always, if you've got any questions, just ask. Thanks, guys.